The Segment Allocation Table, or SAT, maintains a hierarchical record of available and occupied space within the storage layer. The table is divided into allocation units of fixed size, with each unit tracking occupancy state, ownership reference, and modification timestamp. The primary SAT resides in memory as a dense bit-packed structure, while a persistent copy is maintained on disk. Allocation units are organized into superblocks, with each superblock containing 256 units. Superblock boundaries are aligned to power of 2 offsets to facilitate efficient scanning and indexing. The in-memory SAT bitmap uses 1 bit per unit, while the on-disk representation includes additional metadata such as owner process ID and allocation timestamp for audit purposes. Free space lookup operations employ a 2-level search strategy. The first level scans a superblock summary array, which caches free unit counts for each superblock. Upon finding a superblock with available units, the second level performs a linear scan of that superblock's bitmap to locate the first unset bit. This approach minimizes memory reads during typical allocation requests. Allocation operations acquire an exclusive write lock on the target superblock before modifying its bitmap. The lock is held for the minimum duration required to update the bitmap and the summary array. Contention is mitigated through a configurable lock-free retry loop that samples alternative superblocks if the target is busy, distributing allocation pressure across the table. Deallocation follows a reverse process. The caller specifies a unit range via base address and length. The affected superblocks are identified through arithmetic operations on the base offset, then locked sequentially in ascending order to prevent deadlock. Bits are cleared in the bitmap, and superblock summary counts are incremented. The operation is logged to the transaction journal before releasing locks. The SAT supports a configurable allocation policy parameter, defaulting to first FIT. Alternative policies include best FIT, which searches the entire table to locate the smallest adequate free region, and worst fit, which selects the largest available superblock to reduce fragmentation. Policy selection affects query performance and memory utilization patterns over time. Fragmentation metrics are computed by scanning the superblock summary array at configurable intervals. The system records the count of fragmented superblocks, defined as those with free units but insufficient contiguous space for the largest active allocation request. These metrics are exposed via a read-only statistics table updated asynchronously during low activity periods. Compaction operations reorganize allocated units to reduce fragmentation. Compaction is triggered when fragmentation exceeds a user configurable threshold, defaulting to 40%. The operation copies allocated data within superblocks toward lower addresses, then updates all references to point to the new locations. Compaction runs in a background thread and does not block allocation requests. The SAT persists to disk through periodic checkpoint writes. During a checkpoint, the entire bitmap and superblock summary array are serialized to a contiguous file in compressed format using run-length encoding. The checkpoint includes a header with a version number, timestamp, and CRC32 checksum. Checkpoints are written to a staging area before atomic rename to ensure durability. Recovery from an unclean shutdown begins by reading the most recent SAT checkpoint file. The checksum is verified, and the bitmap is decompressed into memory. Transactions recorded in the write-ahead log after the checkpoint timestamp are replayed sequentially, applying allocation and deallocation operations to rebuild the in-memory SAT state. The summary array is then reconstructed in a single full scan. Consistency between the in-memory and on-disk SAT is enforced through a write-ahead log mechanism. Every allocation and deallocation is recorded in the log before the in-memory bitmap is modified. During normal operation, the log is flushed asynchronously at configurable intervals or when it reaches a size threshold. Log entries are removed after the corresponding SAT checkpoint is safely written. Multi-threaded access to the SAT is coordinated using a reader-writer lock. Read operations for free space queries acquire a shared lock, allowing concurrent searches. Write operations for allocation and deallocation acquire an exclusive lock on affected superblocks only, not the entire table, permitting concurrent allocation in different regions. The lock manager maintains a fair scheduling order to prevent writer starvation. The SAT supports pre-allocation mode, activated by a configuration flag or explicit API call. In pre-allocation mode, the system reserves space for anticipated future allocations by marking units as held but unoccupied. Held units are not released on deallocation of the original owner, reducing allocation latency spikes during predictable workload patterns. Held units are visible in utilization metrics but flagged separately. SAT queries can be filtered by owner process ID to isolate allocations belonging to a specific component. A separate owner index maintains linked lists of allocations per process, enabling efficient enumeration and resource accounting. The index is updated inline during allocation and deallocation operations, incurring minimal overhead. Owner accountability facilitates leak detection and billing in multi-tenant environments. The SAT exposes diagnostic APIs for inspection and validation. A full table scan operation iterates overall superblocks and returns statistics including total free units, fragmented superblocks, and age of oldest allocated unit. A verification operation recomputes superblock summary counts from the bitmap and reports discrepancies, enabling detection of memory corruption. These operations are not suitable for online use and are intended for maintenance only. Configuration parameters for the SAT include allocation policy, fragmentation threshold, checkpoint interval, and superblock size. The superblock size can be adjusted at system initialization to tune performance for specific workload characteristics. Smaller superblocks reduce lock contention but increase memory overhead for metadata. Larger superblocks improve cache efficiency but may increase fragmentation. Default superblock size is 64 kilobytes.